Okay, so we're looking at our third application problem, which is a curve sketch using calculus. And there's a few different aspects that go into this that make this quite a difficult question. What we've got to do first, we've got to write down the domain of y equals log x over x. So we've got to think about the restrictions in place and the domains of each of these. So log x, the domain of log x on its own is that x always has to be greater than 0. And that's going to have the same effect on this overriding function as well, because there's no limit on the value of x, so therefore the domain for this is just that x is greater than 0. It then asks us to find horizontal or vertical asymptote. So to do this, we need to look at the limits of this function. Firstly, as the function tends towards 0, and secondly, as the function tends towards infinity. And just to give you a concept of what this is like, I've got the two graphs of the two functions here, and I'll explain why we've got these here to have a look at. So that's the graph of y equals x. This is the graph of y equals log x. Now, just a reminder, the overriding function we're looking at is, we are looking at y equals log x over x. Okay, now, for this, to help us with this, we need to know a few characteristics of both the functions that we're looking at. Now, y equals x is quite familiar. We should be a bit more familiar now as well with the graph y equals log x. But we want to have a look at this value in particular here, the x-intercept, because we can see what's happening here as we go, so that's x equals 1. As x increases and moves away from 1, the value of y equals log x, the value of y here increases as x increases, and it's positive and it's increasing in a positive way as well. However, if we look at the values of x when it's below that, we can see that it actually, the y value increases in terms of its magnitude, but obviously in a negative direction. So you can see it's very similar to the exponential curve with how quickly it goes in size, but in a negative direction. Now, why this is important, let's have a look, for example, at what happens as x tends towards infinity. All right, so as x tends towards infinity, you can see here that this graph of y equals x is increasing in value, and the graph of y equals log x is also increasing in value. Now, what we've got to remember is we are dividing log x by x, and what we've got to determine here is which is the larger of the two as x tends to infinity, because we're dividing the two. So if we look at the two graphs, you can see that for whenever x is greater than 1, you can see that y equals x is always bigger than y equals log x for any point. So if we pick where x is 5, you can see that y equals x has a larger y value than log of x, which means as x gets larger and larger and larger, then our function y equals log x on x, well, what's happening is the denominator, the x value, is getting bigger at a faster rate than log x. So what actually happens is, as x gets larger and larger and tends towards infinity, the denominator gets bigger and bigger, it gets larger than the numerator. So what happens is this ends up tending towards 0. The value of y will get smaller and smaller because the x value is always going to be bigger than log of x. Now, so what we need to look at now as well is we need to look at what happens as x tends towards 0 from above. So what's happening down here? Now, the thing is, we need to look at the values of this. So log x is negative for a start, and x is still positive in this region. So what we're focusing on at the minute is we're focusing on what happens as x is between 0 and 1. But the actual value of log x is the actual magnitude of log x is far bigger than the magnitude of x itself. So what happens here as x tends towards 0 from above is that log x tends towards negative infinity. And from here, x tends towards, as we've written above, 0 from above. So what happens is the numerator is actually far bigger than the denominator. So what happens here overall with y is y actually tends towards negative infinity as well, because that function, the log x, the numerator, dominates the denominator. So this gives us two asymptotes here. We've got an asymptote that as x tends towards infinity, y tends towards 0, so therefore the y-axis is an asymptote. We've also got here, excuse me, that as x tends towards 0, y tends towards negative infinity, which means we've got the y-axis is also an asymptote. Now, moving on from here, we look at part B. So we asked to find y dash, the first two derivatives, y dash and y double dash. So having a look at y equals log x on x, we can see that this is going to require the quotient rule. Just a brief reminder that the quotient rule we've got here is that y dash is equal to u dash v minus u v dash all over v squared. We've got that u is equal to log x, therefore u dash equals 1 on x. We've got that v equals x, and therefore v dash equals 1, and v squared is just equal to x squared. So therefore y dash is equal to u dash v, so 1 on x times x, which is just 1, minus u times v dash, so 1 times log x, so we just get 1 minus log x, all over v squared, which is x squared. Now, to find the second derivative, we're going to, again, it's using the quotient rule, and if we follow the quotient rule, just to save some space here I'm working out, we should end up with the second derivative should equal 2 ln x minus 3 all over x cubed. So we've got our second derivative here, and we've got our first derivative here. Now, part C is asking us to find stationary points, and to determine their nature. So we find that a stationary point exists when dy on dx or y dash equals 0. So we need to solve our first derivative equals 0, so 1 minus log x on x squared equals 0. If we multiply across by the x squared, we end up with 1 minus log x equals 0. So we solve for log x equals 1. Now, for log x to equal 1, we can just demonstrate this in exponential form, so that'd be e to the power 1 equals x, so therefore x must equal e. Now, however, we do need to test this. And what we can do is we can use, because we've already found it, the second derivative. So that y double dash equals 2 ln e minus 3 on e cubed. Well, ln e is 1, so 2 times ln e is 2 times 1, which is 2, minus 1 is, minus 3, sorry, is minus 1, so minus 1 on e cubed. Now, that is less than 0, so therefore means it's concave down. So therefore, x equals e produces a local maximum. And we need to find our y coordinate. Well, y is equal to, use our original function, log of e over e. Well, log of e is just 1, so we end up with 1 on e, which is e to the minus 1. So therefore, e to the negative 1 is a local maximum. And as you can see, I've actually included a sketch of the final answer here. You can see that there is our maximum turning point there at at e to the negative 1. Now, I've run out of space, unfortunately, here. But we can turn to the next part, which is to find the exact coordinates, and I'll work this bit out over here. Find the exact coordinates of the lone point of reflection. So point of inflections occur when the second derivative is equal to 0. So if we go ahead and try and solve that, so we've got 2 ln x minus 3 on x cubed equals 0. Again, times by x cubed. Across, we get 2 ln x minus 3 equals 0. So ln x must equal 3 on 2. And again, we can rearrange this into index form. So we do with e to the power of 3 on 2 equals x. Now, we need the y coordinate. So when x equals e to the power of 3 on 2, y is equal to, look, using our original function, ln of e to 3 on 2 over e to the 3 on 2. Well, ln e to 3 on 2 is just 3 on 2, so we end up with 3 on 2 over e to 3 on 2, and that simplifies to 3e to the negative 3 on 2 over 2. Okay, so that is that's our point. Now we just need to show that this is a point of inflection, so we need to test for a change in concavity. So using the second derivative, we've got our x value and we've got our second derivative. So our middle value, which we know is our potential point of inflection, is when x is equal to e to the power of 3 on 2. So that we can choose a value larger than that, which is e squared. Or we can choose a value smaller than that, which we know is e. Now when x is equal to e, our second derivative, so using our second derivative, which I'll just make a note of at the side, our second derivative is equal to 2 ln x minus 3 on x cubed. So if we substitute our value of x equals e into this, so if x equals e, we end up with 2 ln e minus 3 on e cubed. Well, ln e is just 1, so it's 2 minus 3 on e cubed, which is minus 1 on e cubed. So we know that that's a negative value, and therefore that's concave down. When x equals e squared, we end up with 2 ln e squared minus 3 over e squared cubed. Now we're only really interested in the denominator. We can bring the 2 down to the front to give us 4, so 4 ln e minus 3 on e to the power of 6. And then from there, ln e is just 1, so we're going to be 4 minus 3 on e to the power of 6, which is 1 on e to the power of 6, which is positive. So therefore that is concave up, and therefore there is a change in concavity. So because there is a change in concavity, our point e to the power of 3 on 2 and our y value, which is 3e to the negative 3 on 2, is a point of inflection. And then the last part of the question is asking us purely to sketch it. So what I've done is I've included the sketch in here to save some time for you. You can see that our point of inflection that we just found out is there, our maximum turning point. To look at it in terms of asymptotes, you can see that as x tends to infinity, you can see that y is tending to 0 from above. And likewise here, as x is tending towards 0 from above, you can see that y is tending to negative infinity. Right, now this is quite a tricky question. There's a lot going on here. It's bringing in a lot of the calculus work we've done previously. It's using some information about the log function and a linear function and how we work out those horizontal and vertical asymptotes. It's asking us to find the first derivative and the second derivative. It's then asking us to find the points of inflection. So it's a good revision question in terms of looking at how we find stationary points when the first derivative equals 0, how we find potential points of inflection when the second derivative equals 0 as well, so not at that point here, over here, and then obviously testing for that change in concavity when we think there's a potential point of inflection to actually double check that it is a point of inflection. So hopefully that's been useful to you, and as I said, it's quite a difficult example to have a look at, but work your way through it, take your time, and ask some questions as you go.